Good morning, dear students. Today we are going to start with the next topic of chapter solid state, that is imperfection or defects in solid. So we will see two type of defects, point defect and line defect, and we have to deal with the point defect. So in point defects again three categories are there: stoichiometric, non-stoichiometric and impurity defect. So let's see. Now in defects in solid you can see a very easy flow chart. Defect in solid is categorized as stoichiometric defect, non-stoichiometric defect and impurity defect. Stoichiometric defect again classified as vacancy defect, interstitial defect, which occur in non-ionic compounds, and Schottky defect and Frankel defect. It occurs in ionic compounds. There is a similarity between the vacancy defect and Schottky defect, but the difference is Schottky defect occur in the ionic compound while vacancy defect occur in the non-ionic compound. Similarly, Frankel defect is present in ionic compounds while the interstitial defect is present in non-ionic compound. Now, non-stoichiometric defect is classified as metal excess defect and metal deficiency defect. So, let's see the detail of all these defects. When we talk about imperfection in solids are of two types and we have to deal with only one, that is the point defect. So point defects are the irregularities or the deviation from ideal arrangement around a point or an atom in a crystalline substance, while the line defect are the irregularity or the deviation from ideal arrangement in the entire row of the lattice points. These irregularities are called crystal defects or imperfection. So here you can see if the arrangement of the particles are there, and if at a particular point defect or imperfection arises, then it is a point defect. And if the imperfection is present throughout the row, then it is known as the line defect. This chapter we are not going to bother about the line defect. We will see about the point defects only. Now, types of point defect. As I told you in the previous slide, stoichiometric, non-stoichiometric and impurity defect. So let's see the stoichiometric defects. When we talk about the stoichiometric defect, these are the point defects that do not disturb the stoichiometry of the solid. It means the ratio of the cation and anion remains same after the defect also. This means there is no disturbance in the stoichiometry of the solid. They are also called intrinsic or thermodynamic defects. Basically, these are of two types: vacancy defect and interstitial defect. Vacancy defect: when some of the lattice sides are vacant, the crystal is said to have vacancy defect. You can understand this with a diagram also in a better way. This vacancy defect decreases the density because the particles it will move away from its lattice site. So there is a decrease in the density. This defect can also develop when the substance is heated, and this is the reason why they are also known as the thermodynamic defects. Interstitial defect occur in the non-ionic compound. Vacancy defect also present in the non-ionic compound. When some of the constituent particles, say atoms or molecules, if they occupy the interstitial site, the crystal is said to have the interstitial defect. And this defect increases the density, or sometimes the density remains the same. Vacancy and interstitial defects, as explained above, can be shown by the non-ionic solids, as I told you. If the vacancy and interstitial defects present in the ionic solids, we call it as Schottky defect and Frankel defect. Let's see the diagrams. When you will see the vacancy defect, you can see here easily one of the particle here, vacancy is created. So if the vacancy is created, then it is known as the vacancy defect. But here you can see in the interstitial defect that the particles occupy its position in between the crystal. These are the interstitial sites. So if the particle trapped in between the interstitial sites, then we call it as the interstitial defects. Next, Schottky and Frankel defect. When we talk about the Schottky defect, it is basically a vacancy defect. As I told you, there is a similarity in vacancy and Schottky. But Schottky defect is present in the ionic compounds. In order to maintain the electrical neutrality in Schottky defect, the number of the missing cation and anions are equal. It means if vacancy is created by the cation, then the same number of anion will also create the vacancy, so that stoichiometry of the compound will be same. There will be no change in its stoichiometry, or you can say there will be no change in the ratio of cation to anion. Like simple vacancy defect, Schottky defect also decreases the density of the substance. Because vacancy is created, a cation and anion will be missing from its site. So if the cation and anion will be moved away, then obviously their mass will be decreased and density will also be less. Schottky defect is shown by the ionic substance. Again and again I am repeating this sentence, in which the cation and anions are of almost similar size. It means their size of cation to anion, size of cation and the size of anion nearly same. For example, AgBr, CaCl, KCl, NaCl. One of the interesting example is AgBr. This is the example which shows Schottky defect as well as Frankel defect also. If you will see the diagram of Schottky defect, here you can see there is a regular arrangement of cation and anion. So if you will see here, positive charge, two positive charges are missing, and the same way two negative charges are missing from its lattice side. So total 2 positive charge and total 2 negative charges missing from the lattice side. Therefore, the electrical neutrality of the crystals will be balanced. But Because of the absence of these two cation and anion, the density decreases. Next is the Frankel defect. This defect is shown by the ionic compound. In this, the size of cation is smaller as compared to the anion. The smaller ion, that is the cation, is dislocated from its normal site to an interstitial site. It is but obvious size of cation is small, and you know if the crystals are arranged, particles are arranged in a crystal, they are arranged very compactly and regularly. So the interstitial space is very less. So here only a very small charge particle can come, and out of positive negative ions, positive charge ions is smaller in size. So it can go in the interstitial site, but not anion, because the size of anion is larger. It cannot fit in this small void or empty space. So it creates a vacancy defect at its original site and an interstitial defect at its new location. This is the reason why the Frankel defect is also known as dislocation defect. It does not change the density of the solid, because the cation and anion, they are not moving out of the crystal, but they are within the crystal. Frankel defect is shown by the ionic substance in which there is a large difference in the size of the ions. For example, ZnS, AgCl, AgI, they are having the difference between the cation and the anion. And you can see a very interesting example, that is AgBr. So keep this thing in your mind. If they will ask the example which shows both Schottky and Frankel defect, the best example is AgBr. You can see in the diagram here, positive charge should be here. So this positive cation is missing from the crystal lattice, but it will move in the interstitial space. So it is not going out or creating vacancy like the Schottky, but it is within the crystal. That's why there is no change in the density, or density remains same. I hope Schottky and Frankel is clear. They are very important and many times it is asked in the exam. So stoichiometric defect is clear. Stoichiometric defect are classified into vacancy, interstitial, Schottky, Frankel. Now second is non-stoichiometric defect. Non-stoichiometric defects are classified into two. First one is metal axis defect. Metal axis defect occur due to two reasons. First is due to anionic vacancy. Metal axis means more positive charges. So more positive charges are possible in two ways. Either the positive charge will be more, there is more number of M positive, metal positive charge, or there will be less negative charges. If less negative charges, then also in crystal the excess of positive charge will be there. You can imagine the example of your class. For example, in your class, if we want to increase or we want to show more number of girls, then we are having two possibilities. Either we can add 2 or 3 girls from the other section, or we can remove the boys from your class. So the number of girls will be more in the class. And if you will add 2-3 girls from the other section, then number of girls will be more. The same way, metal axis defect is there. Metal axis means positive charge should be more. So either you add the positive charge or you remove the negative. In both the ways, you will have the metal excess defect. So metal excess defect due to the anionic vacancy. If you will remove the anion. Alkali halides like NaCl, KCl show this type of defect. When crystal of NaCl are heated in an atmosphere of the sodium, then the sodium atoms are deposited on the surface of the crystal. What will happen? Chloride ion diffuses to the surface of the crystal and combines with the sodium atom to give NaCl. This happens by the loss of electron by the sodium atom to form the sodium ion. The released electron diffuses into the crystal and occupy the anionic site. So what will happen if the crystals are there? For example, you can imagine in this way, your particles are arranged in a crystal, positive, negative, and now we have to do the anionic vacancy. So here the negative charge removed, and instead of that electron will come. So there is a maintenance of the electrical neutrality because electron is there now. And how this electron come? For example, positive charge is Na plus, and Cl is negative charges, Cl minus. So what will happen? If the vapors of Na will come, then there is removal of electron, it form Na plus and it combined with Cl minus. So Cl from here, red spot, will be moved away to form the NaCl, and this electron will enter in the crystal. So due to this electron there is maintenance of the electrical neutrality, but once Cl minus moved away, so density decreases and the electron present in the anionic vacancy is known as F center or Fabre center, and this center is responsible for the color of the crystal. If we have taken the example of NaCl, you know the color of NaCl is white, but when the Fabre center or F center is there, then due to this F center, the color of NaCl becomes yellow. So they impart yellow color to the crystal of the NaCl. Color results by the excitation of these electrons when they absorb energy from the visible light falling on the crystal. Similarly, LaCl pink in color, KCl violet in color because of the F center or Fabre center. Now, metal excess defect due to the presence of extra cation at the interstitial site. So, one of the best example to show this is the crystal of zinc oxide. Here, what will happen? For the metal excess defect, one more extra cation will come in the interstitial site. For example, if your crystal lattice is having the regular arranged particle, for example, this is Zn2 plus O2 minus, Zn2 plus O2 minus. In this way, it is arranged. Now, if an extra Zn will come in the interstitial site, then what will happen? Excess of Zn2 plus ion will come, and in order to maintain the electrical neutrality, Zn2 plus, so 2 electron will also come to maintain the electrical neutrality. In this way, there is extra positive charged ion, and we call it as the metal excess. They are also colored due to the presence of these electrons. Previously it was the F center. Here it is the extra electron. Second category is the metal deficiency defect. There are many solids which are difficult to prepare in the stoichiometric composition and contain less amount of the metal as compared to the stoichiometric proportion. A very typical example is FeO. You can see in many books the ratio of Fe and O. In this, Fe2 plus cation are missing, and instead of Fe2 plus, Fe3 plus ions are present in its place, and due to this there is deficiency of Fe metal on the original site. You can see here F center, diagram of F center which we have discussed. Here Cl minus is missing, and Cl minus is missing, but electron is present here. So because of this anion electron present on the anionic side, this is the F center and reason for the color of the crystal. Now third category is the impurity defect. Here you can see the impurity of strontium in sodium chloride. If molten NaCl containing a little amount of strontium chloride is crystallized, some of the sides of Na positive ions are occupied by the Sr2 plus. So there is no relation between the Na plus and strontium, but in the crystal of Na plus NaCl, strontium will come in place of the cation. It occupies the site of one ion and the other site remains the vacant. So the cationic vacancies thus produced are equal in number to that of the strontium ion. Same example you can see in the cadmium chloride and silver chloride. So this type of the defect is known as the impurity. Here strontium ions are impurities in the sodium chloride ions or sodium chloride crystal. Now impurity defect can be seen in the covalent compounds, and we call it as electron rich impurity and electron deficient impurities. It gives rise N type of semiconductor and P type of semiconductor. So these two terms you will see in the physics also, and with the N type and P type of semiconductor, some logic gates and many things are there. Here you will see how N and P type of semiconductors are formed. So, silicon and germanium belongs to group 14. You know it very well. They are the members of the carbon family and have 4 valency. So, 4 valence electrons are present. In their crystal, each atom forms the 4 covalent bond with its neighbor. You can imagine the silicon crystal in this way. Silicon, 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 everywhere silicon with the 4 bonds. When one of the silicon doped with 15 group element. Now what is doping? Doping means addition of impurity, and sometimes this doping takes place intentionally to form the semiconductors. So instead of this 14 group element, if 15th group element like phosphorus or arsenic contains 5 electron occupy the lattice site, then what will happen? This phosphorus will form the 4 bond of the silicon, but 1 bond will be extra, 1 electron will be extra. So wherever silicon get replaced by the phosphorus, 1 extra electron will be there. So 4 out of 5 electrons are used in the formation of 4 covalent bonds with the 4 neighboring silicon atom. 5th electron is the extra and become delocalized. This delocalized electron increases the conductivity of doped silicon crystal. Here the increase in conductivity is due to the negatively charged electron. Hence, silicon doped with electron rich impurity is called N-type semiconductor. Next in the category is electron deficient impurities. In this, silicon or germanium can be doped with 13th group element like boron, aluminium or gallium, which contains only 3 valence electron. So as you know, if the silicon crystal is present, this silicon crystal can be doped with boron. So one of the silicon gets substituted by the boron. So 3 valencies will be same, but one will be missing, and electron hole or electron vacancy will be present in the fourth side. Due to this hole or electron valency, the conductivity get increased. So an electron from a neighboring atom can come and fill the electron hole, but in doing so, it would leave an electron hole at its original position. If it happens, it would appear as if the electron hole has moved in the direction opposite to that of the electron that filled it. So here the electron holes are positively charged and moving towards the negatively charged plate. So this type of semiconductor are known as p-type semiconductor because of positively charged or positive electron holes. You can understand this with the help of diagram also. This is a perfect crystal. Now, if n type of semiconductors are there, you can see this silicon get replaced by the arsenic. So, negative electron will be there. This is known as n-type semiconductor. And if the silicon get replaced by the 13 group boron, then it form the positive hole. So this is known as the p-type semiconductor. So in this way, impurity can be doped to form n and p type of semiconductors. I hope it is clear to all of you. So here your chapter ends. 2 more topics are there, that is electrical property of the crystals and magnetic properties of the crystal. These 2 topics are deleted this year due to COVID-19. So we are not going to discuss about the electrical and the magnetic property of the crystal. So here this is all about the solid state. Next we will start the another chapter of physical chemistry, that is solution. Thank you. Have a nice day. Please keep revising and solve NCERT.